Greetings. This is the fourth lesson in a series of short lessons on basics of power systems engineering. This lesson covers Kirchhoff's current and voltage laws, also collectively known as Kirchhoff's circuit laws. Two fundamental laws of electrical circuits are Kirchhoff's current law, also known as KCL, and Kirchhoff's voltage law, which is also known as KVL. KCL states that algebraic sum of currents flowing into a node is going to be zero. I'm showing 5 currents here, all into the node O. What it says is that their sum, it has to be equal 0. This law is based on the conservation of electrical charge. There's another way of expressing this KCL law, which is equivalent to the first statement, and it says that the sum of currents into a node equals sum of currents out of that node. Here I am showing 3 currents, I1, I2, and I4, going into node O, So I1 plus I2 plus I4 will have to be equal to sum of the currents coming out of the node, which are this one and this one, I3 plus I5. As you can see, the KCL gives us an equation for any node that we look at. So if in that node the currents for n-1 branches are known, then the last current, the missing current, can be calculated based on this single equation that comes out of KCL. Kirchhoff's voltage law, or KVL, states that the algebraic sum of all voltages encountered in going around a loop is going to be 0. And this law is based on the conservation of energy. I have assigned voltages such as V1, V2, Vs, etc. to elements of this circuit. I'll write the KVL for the first loop from the left, which is this one. And I had to also assign a direction. That direction is arbitrary. It could be counterclockwise or clockwise. I took the clockwise direction. And because we are looking at the algebraic sum, we have to decide if we're going to assign a positive sign to a voltage rise or a voltage drop. I typically take the voltage rise to be negative and the voltage drop to be positive. So in this loop, starting here, I'm going to write negative Vs1 because Vs1 represents a voltage rise from negative to positive. V1 represents a voltage drop, so I'm going to assign a positive sign to that. And V4 is also representing a voltage drop, so I'm going to add that with a plus sign. And that has to come to 0 because I've gone around the loop and reached the original point. Here I'll write the KVL for the larger loop indicated in this diagram. This is the entire loop with the direction again clockwise. Again, you can start here or you can start anywhere on this loop. I'm starting here again with the same convention as negative for voltage rise and positive for voltage drop. So we have negative Vs1. Next one along the path is V1, and that's a drop, so plus V1. Next one along this path is V2, and that's also a drop, plus V2. The next one is a voltage rise, negative to positive V3, so I'm going to make that a negative V3. The next voltage is a drop of V6, so plus V6. And the last one before we get back to the starting point is Vs2, and that's also a that's also a voltage drop. So I'm going to call it plus VS2 and set the total sum to 0. As in the case of the KCL, there is another way of expressing this law, the KVL, which is equivalent to the first statement on previous slide. This second way of stating it says that in going around the loop, sum of voltage drops equals sum of all voltage rises. And again, I'm going to use that same loop, the large loop, except use it in this way to write all of the voltage drops on one side of the equality and all of the voltage rises on the other side of the equality. In this case, I don't need to apply a negative sign to either one of these. I'll just use their magnitude. So going around the loop, I'll look at all of the voltage drops. Starting here, this is a voltage rise. So I can ignore it for now and come back to it, or I can put the voltage rise on the right hand side as I go, and voltage drops on the left hand side of the equal sign. So that would be V1. Next one along the path is V2, which is a voltage drop, so I'll put it on the left hand side. V3 is a voltage rise, so I'll put it on the right hand side. Notice I don't call it negative V3. I'll just use this magnitude, but keep it on the right hand side where the voltage rises are. Next is another drop, so that goes on the left hand side, plus V6. Next is a voltage drop, again, VS2. And at this point, I am back to the starting point. So the equation is complete. If you again look at the voltages around this path, you see that there is one voltage rise and two voltage rises. Just double checking my work, and those show on the right hand side. There is 1, 2, 3, and 4 voltage drops, and they're all written on the left hand side. Again, just as in the case of the KCL, if I had all of these, if I knew the values of all of these voltages except for one, this equation will allow me to find that unknown voltage. Let's look at an example in which I'll use the KCL to find the missing currents in a circuit. For the circuit of this example, I have pre-calculated the currents and voltages, but I'm showing only 3 of the currents as seen here, and none of the voltages except for the source voltage, which is 100 volts. Let's use the KCL to find the missing currents, namely those flowing through the 25 ohm resistor, through the 15 ohm resistor, and through the 20 ohm resistor. Since node A over here has 3 branches connected to it, and the current of the 2 of the branches are given, you can see the current in this branch moving toward A and the current in this branch flowing away from A. The KCL allows us to find the third current, which is the same one that goes through the 25 ohm resistor, the current in this branch. To find the current in the 25 ohm resistor, we write the KCL at node A, which says that the 5.254, which is coming into the node, has to equal the sum of 3.586 plus the unknown. I'm just going to call it X. So if this is my unknown current, it's going to be the difference of 3.256 and 3.586. I show that on the next slide. Doing the subtraction, you see that the current here is going to be 1.668 amps. And I've written that out here. Focusing now on node C, there are two currents flowing into the node. And so the current of branch CD, this one, has to be equal to the sum of those two currents coming into the node. The only current going out of the node has to carry the sum of the two. And you can see that sum here results into 2.836 amps for this branch from C to D. And now for node B, current of 3.586 is flowing into it, and current of 1.168 is flowing out of node B. So it makes it allows us to calculate the outgoing current from point B to D as the difference of these two. So much is coming in, part of it is going out this way. The difference has to be flowing this way and into this branch. So by subtracting this current from this current, we'll find the current in BD in the 20 ohm resistor, and that comes to 2.48418 shown here. Now that we have all of the missing currents, remember we were given this, and this to start with, and we found this and this current along with their directions. We can do a quick check on our results to make sure that we haven't made a numerical mistake. There's one node D that we haven't looked at, but we have the currents in and out of that node. The two currents coming into that node are this one, 2.836, and 2.418 from this direction and from this direction. The current that's going out is also known out of node D is also known to be 5.254 amp, because that current that's going into node A is the same current that's coming from below the voltage source. So this current is also 5.254. They belong to the same branch. So the sum of these two has to be equal to this current. And I'll show that on the next slide. You can see 2.368, 2.836, which is this one, plus 2.418, which is this one, adds up to 5.254. So it checks out. The next example you're going to see is not about KCL or KVL, but uses Ohm's law to find the voltages across each resistor in this circuit. This is in preparation for working with the KVL in example 3. But before going there, I would like to take a few seconds here for an introduction and then continue with the rest of the lesson. My name is Fouad Alvandi. I'm a PE in electrical engineering, licensed in the state of Maryland. This is the fourth lesson in a series of lessons on basics of electrical power engineering that I have published on YouTube. You'll find my name and email address here. Email address is fouad.albandi@yahoo.com. You can visit my website at the link on this page, own-your-destiny.mylearnworlds.com, and you'll find comprehensive modules on important topics in power systems engineering on that website. I'll now continue the lesson with example 2. We're asked here to find the voltage across each resistor Starting with the 3 ohm resistor, the voltage is determined by multiplying the current that goes through it times the resistance of 3 ohms, and you see that here. So the voltage across the resistor is going to be 15.762. If the direction of the current into a passive element such as a resistor is known, the voltage that's calculated will have to be polarized in this way, with the positive end, with the end that the current enters the element marked as positive, and the other end of the element marked as negative, which is what I've done here on the next page. Plus, minus, because the current, which is not showing now, was in this direction. For the 10 ohm resistor, again we have 10, which is the resistance, times the current given here. 10 times 3.586 gives me 35.86 volts. Again, given the direction of the current, the voltage is going to be plus or minus in this direction. And you see that here, for the 25 ohm resistor, again, product of the resistance times the current with this polarization, plus or minus. And that comes to 41.7 shown here. For the 20 ohm resistor, we have this one, we have 20 times the current, given 48.36 volts in this direction. And that's given on this page. For the 15 ohm resistor, I have this current times 15 ohms, and that comes to 42.57 volts. And finally, for the last one, 5 times 1.168 gives me 5.84 volts here. In the next example, we'll verify the KVL for some loops in this circuit. I'll pick a loop randomly. Let me take this smallest one in the clockwise direction. Again, that's just my preference. You can use counterclockwise direction if you want. I'm going to use the sigma V drop equals sigma V rise form of the KVL. So going around, I'm going to write all of the drops on the left hand side and all of the rises on the right hand side, starting randomly from here. The first voltage encountered is a 41.7 voltage drop, so that goes on the left hand side. The next one I come across is 5.84 volts, but that's a rise, so I'm going to put that on this side, on the right hand side, 5.84. And the final voltage that I come across is another voltage rise of 35.86, so I put that also on the right hand side with a plus sign. Here we don't use negative signs if we're using this form of the equation. So we just verify that this plus this comes to 41.7, and that's easy to verify. Let's move on to take another loop. This time I'm going to take this largest loop here, and in that direction. Let me start here. The first one is a voltage rise, so that is going to be on the right hand side, 100 volts. Next one is a drop, so that goes on the left hand side, 15.762. The next one is another drop as 41.7. The next one is another drop, 42.54. And we're done. We're back to where we started from. Let me double check. 15.762 on the left, 41.7 on the left as well, and 42.54 also on the left. And the only voltage rise that we have is 100 volts. So if you add these three, they should add up to 100. Again, I'll leave that for the student to verify. And let me now pick a more complicated loop. The loop doesn't have to physically exist there. In other words, it doesn't have to be this one, this one, this one, or the big one that I just picked. You could just imagine your loop to go, let's say, from here to here, back through here, and through here, and over. So the elements that are on this loop are going to be this one, this one, this one, this one, and this one. Again, all of the drops on the left-hand side, all of the rises on the right-hand side. So starting here and coming back to it, 15.762 on the left plus 41.7 minus, or not minus, but on the other side, let me just write the voltage rises on another line because there's not enough room. So the voltage rise of 5.84 goes here, voltage drop of 48.36 goes with those, and finally voltage rise of 100 goes on the right hand side. So these two have to add up to be the same, 105.84. And if you add these together, you should also get 105.84. Double checking again. The starting over here, 15.62, 41.7 as another drop, 5.84 as a rise goes here, 48.36 as a drop goes here, and finally 100 as a rise goes with the other voltage rise. We have now reached the end of lesson 4. This is Fuad Albandi, the founder of educational group Own Your Destiny. Thank you for watching my presentation, and I hope to see you in another one of my lessons.